Before we discuss the boundary conditions for the crank, we need to understand the concept of traction at the boundary. That's what I'll try to unpack here. And I'll go to a simpler situation where I just have a beam like that and fixed over here and some force applied at this boundary. And what I'm trying to get at here is that this, when you're imposing this kind of a boundary condition at this boundary, that's analogous to the flux boundary condition that we had in our 1D finite element example in the big ideas section. So there we had in our 1D example, we had a temperature boundary condition here, and we had a flux boundary condition here that essentially set the gradient of the temperature. And that's a natural boundary condition that's not satisfied exactly in FEA, and that boundary condition is analogous to that. That's what I want to kind of give you an intuitive feel for. And to see that, consider a vanishingly small chunk of material like that at the boundary. And I can write the force per unit area, which is called the traction. So if I have a force like this, and if I divide it by the area, I get what's called the traction. In this case, the traction would just be, if this is a constant force, then the force per unit area at that location is just the value of the force, and you need the components, the vector components, times the area of the boundary. So if I apply a constant force at that boundary, that's going to set the traction for a little chunk of material like that. And the traction is a vector, so it has an x component and a y component. And to see how that affects the stresses, let's zoom in on this little chunk of material here. That's what I've done here. And this is a special case where the boundary is aligned in the y direction. So if I look at this face, okay, that's analogous to that. This is the force per unit area in the normal direction, and it's at a boundary that's aligned along y. That's nothing but sigma x. So that's really setting sigma x at that location. Similarly, if this is the tangential force per unit area on a plane that's aligned along y, that's nothing but tau xy. So tau xy, you're setting tau xy to be equal to the y component of the traction. So in this case, on this boundary, such a boundary condition is imposing a condition on the normal stress sigma x and tau xy, but it's not imposing any condition on sigma y. As opposed to over here, okay, if I consider this boundary, and in that case, the traction in the x direction is like that, and so let's say this face corresponds to that, and so that's Tx. But that's also the force in that direction, the tangential force in that direction, or stress, is tau xy. So depending on how the boundary is aligned, the x component of the traction is setting sigma x or tau xy. And if you have the boundary at some arbitrary angle, okay, and then you're considering a chunk of material like that, you can show that it's going to set a combination of sigma x and tau xy. So in this case, Tx will set a relationship that involves both sigma x and tau xy, and this depends on the orientation of the boundary. And what I discussed here, these two are the limiting cases. You can there's the Cauchy formula. Some of you would have seen the Cauchy formula, and you can derive what these normal components are and so on. And from the Cauchy formula, it was difficult for me to get an intuitive feel for what's happening at the boundary, and I've seen students falling into the same situation. So that's why I'm trying to give you kind of a non-rigorous but an intuitive feel for what's happening at the boundary. So what that means is that, the tractions are setting the stresses at the boundary are giving you relationships for the stresses, and the stresses are related to the strains, which in turn are related to the displacement gradients. In this case, it would be, du dx and dv dy. That means that's like a complicated condition on the displacement gradients, and that's why that looks like that. And so it's much more complicated, the relationship. And also you have three, in 3D you have three components of the traction. So you have three relationships like this coming on the displacement gradients from the, putting like a simple boundary condition on that. ANSYS will take care of all the bookkeeping, but this is something to keep in mind, why this is a natural boundary condition, and it will only be satisfied approximately.